Hello, everybody. My name is Jacob Gonzalez. I am from Laredo, Texas. I'm a chemical engineering major, and I'm currently aspired to get my PhD in chemical engineering and specialize in sustainability. And that kind of leads me to why I chose this topic. As you can see here, this is the production of biodiesel from chicken skin, and that just focuses on the sustainability of fuel sources and trying to get away from fossil fuels and sticking more to something that's both biodegradable and comes from biological materials such as chicken. So we can use this leftover compound to create a literal fuel. Most of this research was done through Science Direct articles. We got a lot of Science Direct articles, composed them, came up with solutions, and we were able to solve this problem and give it to the depth which it's needed. So I just want to start by giving a couple of acknowledgments to Cristina Lopez and Anthony Evangelista. Reason being is that there was a lot of technical questions within this project, and there was a lot of technical work within this project that we had worked together on to create this solution and just to come up with the theoretical process and all these numbers. You're going to see that there is a lot of numbers in this. While this is like a theoretical process, we do have real numbers to the theoretical process, and it was tested very vigorously. We used proper thermodynamic methods and we used the appropriate simulations used within the chemical engineering industry to create our theoretical plan and our theoretical process. So while I do say theoretical, do keep in mind that this was done very intensely. It was strictly monitored by a professor, and it is something that makes sense, as we also saw within articles that they were doing something of a very similar method that we were doing. So quick little overview, like I had mentioned, biodiesel is a biodegradable fuel source and it could be used in place of conventional diesel. It is also used as an additive for conventional diesel. Now they're typically doing 70-30 or 80-20% mixes of diesel and biodiesel. The fatty acids located in cooking oils and animal fats both provide the necessary compounds to produce biodiesel. So we could have used waste cooking oils or animal fats. The reason why we decided on chicken skin as the primary as the primary fatty acid source is because chickens have this main fat compound called trehalene, as you can see there, and trehalene is arguably the best fat for to converge into biodiesel. So we chose chicken skin because of the best conversion percentages that we could get from the actual fat. And this process combats both environmental pollution and corporation waste. Reason being is that there's a lot of chicken production. There's a lot of chicken production within the United States or just global, and we help take away some of their waste chicken skin that they might either they might send to farmers so that they could feed their livestock with, such as pigs and other animals that would eat that chicken skin, or B, they could send to us as a chemical plant and we convert that into biodiesel. So a couple little engineering standards that we had followed throughout this project slash technical report was we used Aspen Plus. Aspen Plus is our simulation software that we use to do the theoretical process of the production of biodiesel. So we use this whole process to simulate it. You're going to see a good little snippet picture of something that you would see in Aspen Plus, and that you're going to see that picture in our process flow diagram. Heuristics, we also used heuristics. Heuristics is basically a table that tells you the standard size or the real life size of certain units and vessels, just to make sure that when we're doing our calculations and saying, okay, we need this many vessels, okay, we need them at this size because of how much volume or liquids we're inputting into stuff, we made sure to follow what matches in the heuristics tables, just to make sure that we're like, okay, we don't come up with a unit that is just unrealistic in size and or dimensions of diameter and length. We also used process design illustrations such as the PFD and the PNID. This basically creates a concept. This basically gets the theoretical design and it makes an image out of it, just so you can wrap your head around what we're actually doing a little bit more. And you're going to see a couple slides with those pictures, as well as we talk about the environmental treatment. How are we going to dispose of our chemical waste, and what methods and what's best for our disposal. So let's get straight into it, starting with our target production rate. So we wanted to reach around 470 million gallons per year of biodiesel, which is around 11 million barrels per year. We took these numbers from a model plant in Port Arthur, Texas. It is actually a Valero plant, and we wanted to do this because we wanted our plant to be stationed here in Texas. So we used these theoretical numbers and used the Texas typical land costs and stuff like that. So we made most of our economic analysis through the plant being in Texas. And it's pretty viable to make this much biodiesel. After we did a couple calculations and we used some of the Tyson's numbers of how much fat they use, we are only taking around 0.02% of the yearly production, the yearly fat production of Tyson. So we are not taking a lot of fat. It makes sense that to make a biodiesel production plant because we have enough feed materials to create and to make and reach our target production rate of 470 million gallons a year. This plant is going to be active for around 290 days out of the year. There is going to be two 30-day turnarounds where a turnaround is, long story short, is whenever there's some sort of issues, you postpone them until a turnaround and you order all the parts, get everything ready. When the turnaround starts, the plant shuts down for 30 days, and within those 30 days, every single repair that needs to be made tries to get done within those 30 days just to increase the efficiency of production. As well, we were going to give ourselves 15 extra days in case of any unexpected incidents, whether it would be something hazardous or we have to close because of some other event, just any unexpected incidents that we didn't foresee. So this is a little product market. So here we have our main product, which is our biodiesel. And we also have a byproduct, which is glycerol. Glycerol is just made. We weren't trying to make glycerol, but it just ends up happening. So as you can see here, the majority of the percentage of biodiesel is going to go to diesel engines, also utility and effective solvents. Glycerol is a little bit more split up. It could either go to the cosmetics, the pharmaceutical, or the medical industries. So you might hear this word be thrown around here and there. It's called transesterification. Transesterification is the chemical reaction where an ester is altered by the presence of an alcohol in the catalyst, and you produce something called a fatty acid methyl ester, and that is the whole reaction. That whole reaction is just called transesterification. So an ester is typically a fat, like triolene or the chicken skin. The alcohol we're going to use is methanol because it's a cheap alcohol. The catalyst is going to be our potassium hydroxide. And that fatty acid methyl ester, that FAME, is going to be our biodiesel. Within this reaction, you just have a natural byproduct that happens, and it is called glycerol. Good thing is that, like I had shown you in the product market, there is a pretty high demand of glycerol at high purities, so we can also sell that byproduct for good money. So this is a little process concept diagram. This is just a little slight illustration showing, okay, you're inputting your alcohol, your methanol, you're inputting your ester, your triolene, and you're coming out with your biodiesel, which is your methyl oleate, and your byproduct, which is glycerol. So here, this is a process flow diagram. As you can see here, this is a typical, so it's something you would see on Aspen Plus. This is more of the actual theoretical of, okay, we're inputting this into our feed. Okay, we're putting this into a reactor. Okay, after this reactor, we're separating it with water. After we separate it with water, we're turning it to these condensing towers or these distillation towers. Then from there, we're separating them upon boiling point and stuff like that. So this just shows what the actual simulation goes down and what happens. So for process safety, the reaction is exothermic, which means it releases heat. So that means that all the reactors have to be jacketed and make sure we're running some sort of cold liquid to make sure we maintain a constant temperature and there is no pressure or temperature buildup. Emergency relief valves will be installed in all the reactors just in case there is too much pressure buildup and we don't want a vessel to explode, so we would just release the vessel. It might be a leak, but it is better than causing major vessel damage and or just having flying shrapnel fly everywhere. It's safer to have a slight leak and contain that leak and then deal with that portion. So the HAZOP analysis of the reactor block, we did that to follow the process safety. Here is the table. I'm not going to go too much into it. You can see there's a lot of information. This is, long story short, showing a table of things that can go wrong within a reactor and what would happen. However, these are very unlikely because multiple instruments have to fail, and there's always going to be typically a backup instrument just to make sure if this goes wrong, we have this. Let's go into the sustainability and the treatment of it. So most of our chemicals aren't too hazardous. We do have methanol, which is very flammable, and potassium hydroxide, which is our catalyst. We're going to be dealing with that in very small amounts. That's very poisonous and dangerous to our health. There should be little to no exposure of the potassium hydroxide that will stay in the tank and it won't come out of the tank. So we plan to incorporate recycle streams. However, we were running into some Aspen trouble, so we weren't able to completely incorporate those recycle streams. A recycle stream is you get on the any unreacted feed materials that gets pushed through the reaction would basically just be looped back around to be fed back into the reaction in order to reduce the amount of materials we have to buy. We also used a washing column. This uses large amounts of water, and it's pretty ideal for recycling just because since it is water, we can just separate that and resend that water and just keep using that same water to flush and separate our water miscibles and our water immiscible chemicals. As well as treatment. For treatment, we're going to either be using an activated carbon treatment. Since most of our stuff is biological, we could use activated carbon to eat up that and just take out those biological anything that was biological in that water so that it can be dumped and it will be clean. Or we will use an aeration basin, which is basically just open to the sun, and with a little bit of mixing, some bacteria, or called in the industry bugs, they'll eat the biological material. Anything that floats to the top should get evaporated through the sun, and that water will be clean. So I'm not going to go too deep into the kinetics. The kinetics is pretty complicated. Long story short, the kinetics basically describe at which rate the reaction would happen and what feed materials, at what concentration and what ratios do you have to feed them in order for you to be able to produce biodiesel effectively. I'm not going to go too much into this. This is a summarized stream tables. Like I said, there's a lot of numbers, there's a lot of streams, there's a lot of pipes. This just shows typical temperatures, pressures, mass flows. This shows the equipment, the sizing, how many equipments you're going to need, what temperature, what pressure does it operate at, what is its names. Here we have more equipment, same thing, sizing per unit, number of units, pressure. These are our unit costs, how much each unit would cost, and what would be our total amount. This is our cost of our materials. Basically, on our left, we have our feed materials, things that we're going to be putting in, and things on the right, we have our product, which are things we're going to be selling. As you can see here, some of our products is more than some of our costs. So it makes sense that as we are putting in these materials, they become more profitable, and that then we can sell for a profit. Our cap cost summary. So this is a little summary of our costs, of how much everything should cost, our total module costs, our grassroots costs, our equipment costs. We did some fundamental heat integration. This is a little summary of our utility costs. So without a heat integration, it's going to be this much. With heat integration, it's going to be this much. And this is the amount saved if we do heat integration. So labor, we have simplified labor, how many operators, how many engineers. This is pretty unreasonable. I feel like for the size of our plant, we might need more, but that's something that we have to tweak and alter and discuss for further work. This is a little bit of their breakdown, what their shift looks like and what it's expected and how they're going to be working. It's typically 4 days on, 8 days off, 4 days, and then 4 days on, 8 days off, then 8 days on, 4 days off, and so on and so forth. This is our economics. We have here our fixed capital investments, and we just have a little bit brief economics. This is our cash flow diagram, just showing a quick little diagram showing how much money and our present worth value and how much it's going to be going. As you can see here, there's a slight decrease because we have to create the plant, then we have a big drop to buy our cost of materials. Then from there, because of our products and how much money we're making, we no longer have to worry about having those drops. This is more subsequent work. We do need to include the recycling streams. As we said, we had problems incorporating those. We need more in-depth economic analysis just because it is pretty bare. Alongside the heat integration, we need updated biodiesel pricing since they are a little bit older. We need to optimize our distillation, and we need to use a different model for our kinetics. This is a little Gantt chart that we use to measure our time, and these are our references. That's all. Thank you.